And so up to this point, we've talked a lot about properties of acids and bases, and we've talked about what makes an acid an acid. It's got an H on the front and can produce H pluses, and bases have an OH on the back, and it produces OHs. And for acids, the litmus turns red, and the pH is low, it's less than 7. And for bases, the litmus turns blue, and the pH is high. And we wrote those properties down right at the very beginning, right? And then we talked very quickly about how strong an acid or a base is. And we talked about pH, and we calculated some numbers with that. And that's where we kind of then took our break, the Christmas break. We did our quiz. And then to finish off this little part of a unit, it's the last part of Unit 2. On Monday, we talked about titrations, which is a neutralization reaction where we react an acid with a base in order to find the concentration of one of them that we don't know. We did the lab yesterday. So today we're going to talk about other reactions of acids and bases other than neutralization. Neutralization is actually in the note as well. But we're going to talk about other common chemical reactions that acids and bases undergo. And it's not a very long PowerPoint. I don't know if you guys can see there. It's only got 6 slides. And then we will watch a little video, which is kind of entertaining. And then there's a little worksheet on some of these reactions. And then when we're done that, we'll be ready to review and then to get ready for the test. So reaction, don't write this down. This is just a statement, right? We just put the title, reactions of acids and bases. Acids undergo a series of characteristic reactions that can be used to identify an unknown solution as an acid. Actually, you can put reactions of acids, because in this case, we're talking just about the acids, all right? Don't write the little bullet. Acids we know have H in common, and so they undergo a characteristic set of reactions. So the head title was reactions of acids and bases. Now we're going to just talk about reactions of acids. And the first one is reaction of a metal and an acid. And I will complete those reactions with you in a moment, once you get everything written down. So this is actually not a bad little also review of what we're going to need to know for the exam. Remember, we talked about single displacement reactions where one element switches out another element that's found in a compound. So it says there an active metal will react with an acid in a single displacement reaction to produce hydrogen gas and a salt. Now, when we did single displacement reactions, we looked at something called the activity series. And it has a list of elements. And it's that list that has the really reactive ones at the top and then the ones that aren't reactive at the bottom. And I told you to guide your eyes to the bottom of the list, and gold is at the very bottom of the list. And gold is so unreactive, it wants to be alone, right? Remember that statement? The elements at the bottom like to be as their atomic state in their solid state. So gold wants to be alone. Gold is not an active metal. It does not participate in chemical reactions, right? That's why we use it in jewelry. We sometimes even use gold in special circuitry that we want to be very stable. So it's a very, very stable atom. It does not react. But if we go higher up in the activity series, I don't know if you remember, but hydrogen is in the activity series about 2/3 of the way down. So if you go above hydrogen, anything above hydrogen will want to react. it's going to switch places with a hydrogen. So an active metal is anything that's near the top of the activity series. So magnesium, we take a look for magnesium, it's about 1/3 of the way down. It's not a big deal, but it is definitely above hydrogen, so it will react with the H and swap it out, all right? Potassium, also above the hydrogen, it will react and swap it out. So that's what we mean by active metals. And I didn't orient the board. Let's see if I can keep going. Not bad, it'll work. So I'm just going to draw this in. Here we've got that single displacement reaction, all right? It's going to result in a magnesium chloride. Now, don't forget, we always have to cross over in order to get the complete formula. Magnesium 2, chlorine -1. So what do I have to do to complete this formula properly? Yep. MgCl2. And hydrogen is by itself, but hydrogen is one of those special gases. Does anybody remember what I need to put there to complete it? Yep. H2. Excellent. And now if I need to balance this, I believe I need a couple of these HCl's in order to take care of the 2 H's and the 2 Cl's. So I need 2 of those. So if you put some magnesium metal in some acid, it'll actually start to bubble, it'll bubble away, and those bubbles will be hydrogen gas. We can do the same with the potassium. You could probably go ahead if you wanted to give it a shot. I'm not going to do the loop this time, but the K is going to go with the sulfate. Again, we've got to check to cross it over. Check that for me to see if I need any extra numbers. And the H goes by itself, and there happens to be 2 of them there, so that works out nicely. Do I need anything to complete my first formula? Yep. Yeah, it's K2SO3. Right, this is actually sulfurous acid, but that's okay. And I believe I need another 2 in front of the K in order to balance it up as well. Whoops, I missed the writing there, and now I'm in trouble. Now I'm in trouble. What the? This thing is in the way. Oh man, I'm not gonna be able to write a 2. Oh, I know why. It's because I'm not on the board. Here we go. One more shot. More shot to put a 2. Nice. Okay. All right. So metals that are above hydrogen on the activity series will single displace to produce hydrogen gas. And notice it says a salt. And remember, I've talked about this before. The term salt in chemistry just means an ionic compound. It doesn't necessarily mean table salt. So any ionic compound like we've got in these 2 examples count as a salt. All right. Now in the video that I'm going to show you, we're going to see examples of these reactions. Reaction of a carbonate with an acid. Again, I'll let you write this all down. We've got 2 blanks to fill in here, right here after the double displacement, and then the overall reaction at the bottom. reaction of a carbonate with an acid. An acid reacts with a carbonate in a double displacement reaction to produce carbonic acid and a salt. Now, carbonic acid is one that we've encountered in class in discussions already. Does anybody remember where we find a common source of carbonic acid? Yep. Yeah, it's in pop, right? So we all know that when you open your bottle of pop, what does it do? Okay, what if you shake it and then open the bottle of pop? Nobody's going to answer. It fizzes up. It makes bubbles. Makes lots of little bubbles. Thank you for not answering. Anyway, so it makes lots of bubbles. That's exactly what this reaction does. Now, this reaction, and I've talked about it probably before, this is the classic volcano reaction. Did we talk about the volcano reaction? And how if you watch Disney and we got to talk about all that good stuff about, about recess and all that? Right. That's the same reaction, except we're going to just write it down this time. When you do the volcano reaction, typically you use sodium bicarbonate. Again, it has a carbonate in it. That's baking soda. And typically you use vinegar. Why? Because you have them in the house and you can mix them together quite easily. In my example that I'm doing here, HCl, right, hydrochloric acid, and I have hydrochloric acid across the way. You would, again, have to get like muriatic acid if you wanted that. And calcium carbonate. Calcium carbonate is found in chalk. So chalk is calcium carbonate. Marble, like if you have a marble top, it's calcium carbonate. Now you might say, if I spill vinegar on a marble top, why doesn't it fizz away? They put a protective coating on there that isn't reactive to keep that from taking place. Anyway, so this should fizz. So let's explain why it fizzes. First, we have a double displacement reaction. Again, the front guys swap position just to remind us of how a double displacement reaction takes place. It's going to get me an H with a CO3, and again, we have to cross over to get our formula. So you need to find your carbonate. Hydrogen is in group 1. So do I need to add anything to this? What do I need for the formula of the hydrogen with a carbonate? Because I got to cross over. Take a look at your periodic tables. Yep. Yeah, I need an H2CO3 because carbonate is -2. And then I'm going to have the calcium with the chloride. And again, I have to cross over if needed. And I'm kind of forcing you to do this because we have to do this for, the exam and tests. Yep. Yep, CaCl2 because calcium is 2 and chlorine is 1. And then I need to balance. What do I need to balance this up? Yep. Yeah, and look at how I've done that on the screen. That's downright evil. I don't even know how I'm going to squeeze that in there. Can I make a tiny little 2 in there? Look at that, baby little 2 in there. That's fun. Hopefully you guys left some room for a 2 in front. So there's the initial reaction. Now, does that produce bubbles? Well, it's this decomposition. Carbonic acid is made by injecting carbon dioxide into water. That's the reverse reaction. So when you have carbonic acid formed, it goes the other way and it lets the carbon dioxide out. That's a gas, and that's why it bubbles. So to rewrite the reaction, wherever we see H2CO3, we can now put an H2O and a CO2. So it's H2O plus CO2 gas, that's where the bubbles come from, and then calcium chloride, and I still need to balance, and look at there, I still didn't leave a whole lot of room, little 2 in front of that HCl. So I can take the whole equation and rewrite it, and wherever there is an H2CO3, so wherever we have this, we can put that. All right, that's the same thing, except it's fallen apart and it's given off the bubbles. Okay, so if you have an acid on a carbonate, it will break down the carbonate and produce gases. All right. So they can react with metals, they can react with carbonates. There's a second example. Let's do that second example together here. Actually, you can try it yourself for a moment, and then I'll catch up to you. What did you do? You already watching my video? You've jumped too far ahead. Be patient, sir. Be patient. I have a link at the bottom of the PowerPoint to the video. Just couldn't help himself. So again, the H2 is going to swap out the Na, and notice both carbonate and sulfate have the 2's, so that's handy. That's going to end up with H2CO3 and Na2SO4, and you'll notice when you cross over 2 and 2, that one's already balanced. It's nice. So when we see the H2CO3 as a product of this reaction, we can then rewrite it. H2SO4, Na2CO3. This now is H2O and CO2 gas. You don't need the gas in there. I'm just stating that that's where the bubbles come from, and Na2SO4. Okay? Now, bases don't undergo characteristic reactions. They can neutralize an acid. That's what they do. They can also, react with things like skin and various other things, but they don't react with carbonates, and they don't react with metals. So there isn't a long list for bases. So the only one we're going to talk about, and the one we're going to finish off with, reaction of an acid and a base. And that's our neutralization reaction. And you know what? We've already talked about that. We talked about it when we were doing our titration reactions. So this is really just a formal list of this particular reaction, just formally writing it down. Are you entertained by those two gentlemen? They are entertaining. A strong acid reacts with a strong base in a double displacement reaction to produce water and a salt. Because the resulting solution is neutral, this is called a neutralization reaction. Now, we've done double displacement reactions. We've balanced them. We've seen neutralization. I've shown you various techniques in balancing. I'm going to show you another variation of it here. We know that water is going to be one of the products, right? Because the H is going to come into this position, and we're going to get H2O, right? And the other one is going to be the other metal ion that goes with the non-metal ion. In this case, it is, oops, that's terrible. I was going to write the Cl first. KCl. That's supposed to be a K. Oh my goodness, I'm making a mess of it, more of a mess of it. KCl. All right. And when you balance this, think of forming water. It takes one OH and one H to get together to form one water molecule, because one H sticks to the OH and it makes an H2O. So notice here, there's one OH in KOH and there's one H in HCl. That's perfect. That makes one water molecule. And you'll see there, we've got one. So the water is all balanced. And if you do the crossover of KCl, and I'm just going to scribble that out because it's a mess, you'll notice it's 1 to 1. So this is balanced already. It's like a perfect little neutralization reaction. One H gets together with one OH to make one H2O, and KCl is what is left. Let's take a look at this second one. Again, swap them out. You're going to get an H2O. We might have to put a number in front. And then I'm going to get an Na with the sulfate. NaSO4. And we're going to have to cross over if needed. And this one I'm going to have to take a look at. What do I need for this formula for sodium sulfate? Yep. Because SO4 is a charge of 2. Excellent, a 2. Okay, so now let's think about the balancing. How many OHs have I got here? An NaOH. How many OHs are there? There's 1. How many H's are on this acid? There's 2. Well, if I'm going to make some water molecules, and if I've got 2 H's, how many OHs do I need to pair up with them? I got 2 H's. How many OHs am I going to need? I'm going to need 2. So I'm going to need 2 of these in order to take up all those H's. And when those 2 get together with those 2, how many waters am I going to make? 2 waters. So that's a different way of balancing, by thinking about how much water is being formed. Many different ways of balancing chemical reactions. If you didn't like the way I explained that, you can use whatever method that you want to use. But that's one way I like to think of a neutralization. How much water is being formed? How many OHs do I have? How many H's do I have? Do I need to multiply 1 by 2 or 3 in order to balance it? Okay, that's the end of the note, and I'm going to stop the recording right here. Then we're going to watch this little video for a bit, and then I'll let you work. Let me just stop the video first. Oh, I need a keyboard. This is